So if you have access to unlimited quantities of labeled data and have access to unlimited GPU and have unlimited amounts of time to train a AI model, then this talk is not for you and you can go find a different talk to watch. However, if you want to get the most out of your data with the least amount of effort, then I hope I have some things to share with you. My name is Michael Gormish, and I lead the research team at Clarifai. And one of the themes of our research team is data efficiency. How can we do the best with what we have? Because we have some customers that have lots and lots of data but don't want to label it. We have other customers that don't have much data at all right now, although they hope to get some and want to get something going quickly. And so we've built a lot of techniques over the years to make it easy for people to get the best with the data that they have. And so the things I'm going to talk today about are how do we reduce the cost to getting to a sufficient level of accuracy? How do we do things with no data at all, zero-shot learning in some sense? How do we do things with just a little bit of data? Maybe I have an example or two, or I have 5 examples in a class, or I have lots and lots of data but no time to label it. So I'm going to step through all of those, and if you have to leave early, I'll tell you that the last 2 words of the talk are deploy first. So the secret to data efficiency is deploy first. I do want to say a little bit about Clarifai. Clarifai has been working on data efficiency for 7 years now. We were established in 2013 when Matt Zeeler won the ImageNet contest for doing image classification with his models. And we have a variety of sponsors, one of which is NVIDIA. And so we're very happy to, like them, support all sorts of applications and in particular, machine learning applications. The company has won a variety of awards. The one I want to mention is the Forrester New Wave Leader. That's significant to me because basically it ranked Clarifai up with cloud providers, and of those in the leader part of the report, Clarifai was the only one that was really focused on doing AI. Everyone else in that section was one of the big giants that was doing basically cloud services. And so we provide a level of care and customization around your AI that you won't get from the other leaders. Now I want to take a step back and just talk about machine learned computer vision, because I have a personal long history of doing computer vision and of machine learning as well. But I want to talk about the transition that has taken place. So when I was learning computer vision type things, the typical way you made progress in a problem was that you had a graduate student that spent 4 years doing some project, and in the end they came up with the set of equations that was a solution to one small problem. And that has changed to, as we see on the right-hand side, the lower right-hand side of this slide, now a lot of computer vision problems are solvable by collecting a bunch of data, labeling the input, and then teaching a highly parameterized model with millions of parameters how to go from a new labeled input to the desired output. And so that same technique has revolutionized image classification, image segmentation, object detection, image matching, pose estimation, image compression. Just about anything you can imagine has had some success with machine learned computer vision rather than traditional computer vision. In image classification, right, machine learned computer vision took classification error rates from over 20%. You had a contest where they said, hey, amongst these few classes, give me a bunch of guesses, and I'm going to look at the top 5 answers, and we want one of those to be the right answer. And the error rate in traditional computer vision was well over 20%. When deep learning came on the scene, they quickly pushed that down, and now they've had to basically change the contests so that they have more classes in them, so that they're harder, so the objects are not the sole thing. And so this labeling and training a model has made incredible differences. But more so than that, for me, computer vision with labeling has allowed us to do things that really were impossible to do with equations. So we can have machine learned models that find my dog, or have concepts that have love or purity or sunshine in them. And as long as we have a consistently labeled data set, we can generate a machine learned computer vision model that produces those same results. And so that's an incredible capability that no graduate student was going to be able to do with their set of equations. And there's a variety of other things that machine learned computer vision has enabled. But basically, all of this has transitioned the problem from finding the right equation to finding the right data, the right metric, and training that with that data. And so the data becomes very important, and that's why we're going to talk about data today. A typical set of steps to find a solution to an AI problem is to define the problem in some way. Now, usually people skip that section and just sort of jump into a solution that they had in mind. It's also very useful to define meaningful metrics so that you know if you're approaching the right answer. And also underlooked is the importance of defining sufficient accuracy. So if you're looking for an accuracy of 100%, you're not going to be satisfied with a machine learned solution. You're also not going to be satisfied with traditional computer vision methods. They didn't get 100% either, but they didn't feel like there was a problem because they were operating in a very fixed domain, and people writing the equations were very clear about this is just the optimization of an equation, not this wasn't an entire solution to your problem. And I think one of the things that we've jumped to lately is we sort of assume that AI is solving the entire problem. And one of the places that comes up is we basically have to figure out what is sufficient accuracy out of our machine learning system to get the right answer. Anyway, our typical machine learned problem, we collect data. If you're building a Gantt chart for machine learned computer vision, that should be a big chunk of time normally. I'm going to collect a lot of data, then I'm going to label a lot of data, then I'm going to train my data and try out different model architectures and train loss functions and learning schedules. And then finally, I'm going to deploy the models, at which point I will find out that something went wrong, and I have to figure out which step on this big thing I should jump back to. The good news is that most machine learned problems have some sort of curve that looks like this. Basically, we can start training a model, and on the lower curve here, at least lower on the right, we're showing the loss of on our trained data. So we have some neural network that we're optimizing, and basically as we provide more data or more computation, we're able to do a better job, and we're able to reduce that training loss. And at the same time, hopefully we've defined a test set, and the accuracy on that test set is increasing, and it's an interview question for what happens if that's not the case. But for now, let's just sort of assume that we've got a problem where as we apply data, as we apply computation, things get better. Well, the important things about this curve are, first, on the right-hand side of that, what is the accuracy that we have to hit? Are we going to plateau at some level before we've hit the required accuracy? Or are we able to operate with less than 100% accuracy? And what is that percentage? And now, assuming that we can operate with less than 100% accuracy, then we're over here on the left-hand side of this chart. And the question is, how quickly, basically meaning how low cost, how little data, how little training time can we get to this 85% accuracy level? And so I'm going to step through a variety of techniques, as I said, and the Um, the real question is, what's the lowest cost way to get to the required accuracy? And you'll see I've listed a bunch of steps that we can use on the left-hand side of this table, and the amount of training data that's required, the amount of maybe GPU or CPU that's necessary, and also the engineering work, because that's another key thing with the cost, is how much do I have to do to manipulate my data to get to the final model. So in the academic literature, there's a lot of papers that are written with the title zero-shot learning, and they'll define a very formal way to define exactly what they mean by the way that you provide information about your data that isn't actually providing data. Maybe I'm describing an image rather than actually showing an example of the image. I'm just going to grossly simplify and say I want to talk about what to do when you have no data. So zero-shot data is I don't have even a single image of what I want to classify, for example. And so the ways that we'll look at dealing with those is using pre-built models or subsets of pre-built models, or latent space on the outputs of a pre-built model. So Clarifai has built dozens of models using millions of images. So if you have no data, that may be okay. You may be able to use one of the models that we already have. So we have models for celebrities and food and faces and not safe for work activities and demographics. And if one of those is a good match to your problem, that's absolutely the best place to start. And it's a very quick start. In fact, you can start by deploying first. I said that was going to be the last word, 2 words in the talk. Well, that's also some of the words in the middle. I can deploy a model basically by signing up for an account. And if I'm using a pre-built account, I can run this one-line curl command to send an image to Clarifai and get back the concepts that are available in that image. And so I've shown the one line of curl because if you know what you're doing in your language, you can take and translate curl into whatever request library you use. Clarifai does provide a Python, Java, and Node.js, very detailed descriptions on the website with the documentation, but we also have additional clients for PHP, Swift, Rust, Go, C#, C++. And all of those basically do the same thing. They interact with the Clarifai API, and they get you back a list of concepts, at least for an image, and for text, and for other data types. Basically, you upload your unstructured data, and you get back some results. So here's the JSON that's replying to showing the concepts in one particular image that you get back. And so if we're thinking about, I have a project and I don't have any data, then I want to use a model that already has data used to build it. So Clarifai spent millions of images creating models, and now you just use those. If we don't have a specific one of the dozens of pre-built models that fits your case, we have the general model. The general model has 9,000 categories in it, and often those are some of the ones you need, right? So if you can find a subset of those, then it's very easy to filter the responses from the general model and select the results based on the categories there. I like to say that a picture is worth a 10,000 dimensional vector, because basically we actually recognize 10,000 classes, but we don't respond with all of those. There's 9,000 or so that we respond with. But anyway, for each of those categories, each of those concepts, we provide a score between 0 and 1 for your image. So you give us an image and we return a 10,000 dimensional vector of concepts. And you can use those concepts to do additional things. So if you have a database and you want to augment your image with some information about the image, you can just directly use that as metadata enhancement. And you can use those if you have a feature store, you could store those in your feature store. And if you have a structured data AI workflow that you want to follow, then you can use those labels as inputs into the structured data and combine them with other data, time of day or whatever, and build the model on top of that. So with zero image data, you can use a pre-built model, or you can use the general model to get this 10,000 dimensional vector out of it. And you can use the model, that 10,000 dimensional vector, to provide some explainability. One of the things that's important for a lot of AI models is the ability to explain the model. And there's a couple ways you could do that. Clarifai actually did do some of the early work on visualization of the interiors of neural networks. And you can use that to try to figure out what's going on with your imagery when the model doesn't give you things that you want. But frankly, if you think about an end user's position, it's more informative to tell them things about the labels that came back. So in the AI system as a whole, one of the reasons that you didn't get the result you wanted was that the particular class of concept that was returned by the model wasn't the one that you thought it should be. And so that part of the model is explained by using human level terms that the concepts represent. Now I want to imagine that instead of no data whatsoever, we actually have at least one sample of each thing that we want to do. And so again, in the academic literature, you might look for the phrase one-shot learning and read about some special techniques that try to deal with that situation and try to implement them. But what I'm going to suggest that you do instead is make use of Clarifai's visual search. So if I have one example of every type of image that I want to recognize, I can upload those into an application. And then I can search for the closest image to my query image. And I can guess that maybe the closest image to my query image is the one that's in the class that I've labeled. And the nice thing about that is, as I have more examples, I can also upload those with their concepts. I can repeat the search and I'll get more accurate, because basically what I'm doing is, given a query, I'm looking for the nearest neighbor, and the more nearest neighbors I have of each class, the easier it is to get the right answer. And so this works very well if the query images are similar to the sample images and in the same way. However, it doesn't work nearly as well if the sample images that you have are all, for example, from a catalog and they're shot on a white background, and my query images are all from real life. And then when I do this search, I'm more likely to match something that happens to be in the background of the image rather than the object of interest, because the source and the query images came from different things. Now that points us back to the conclusion of our talk, which is deploy first. If I deploy first and I use the general model and I have real images from my end user that I can look at, then I can use those I can label those and do the right thing in my search project. This is an example because this is something that we do all the time. This particular example is showing the Clarifai interface with faces being searched. So I've uploaded a bunch of images from my deployment, and I have a particular one that I want to label, so I search for it, and then I find all the ones that are close to that, and I can label those, which ones are close and which ones aren't. So now I've quickly bootstrapped from the case where I had just one example to the case where I have many examples. But I think it's important to think a little bit about visual search, because one of the important questions is, what are the differences that I want to ignore, and what are the differences that I want to pay attention to? So if I have the query image of a red triangle with a blue border around it, and I'm using that as a search query, then which of these is the closest match? Well, truthfully, I've already biased you towards A, B, and C, because I described it as a red triangle with a blue border around it. But if I just said I'm looking for triangles, you might want item J, Or if I said I'm looking for a red blob with a blue surround, then you might like item E. And so it's important to have enough examples so that the machine learning algorithm can begin to figure out what are the characteristics that we want to pay attention to and what are the characteristics that we want to ignore. And so, for example, we typically assume that a machine learning system should be completely invariant to translation. So we recognize the same object no matter what part of the image it appears in. However, if you're building a safety system and you're trying to detect if a person has entered the restricted area, then maybe you don't want to be translationally invariant, right? I want to recognize where somebody is on where an object is in this image. In image classification, we typically want to ignore things like translation or illumination or rotation. But again, once again, maybe not. Maybe we're trying to distinguish rotated objects. We want to figure out that something is fallen down and is at a bad angle, or we want to figure out size and know whether this is the large size of the product or the small size of the product. So it's very important to be able to have examples of the things we want to be invariant to and the things that we want to discriminate. Once we get enough examples that have some of those characteristics, then we can go into few-shot learning. Once again, you can search the academic literature and find and implement very specific things having to do with that. But we've tried to make it simple. If you have enough examples, then we'll do some transfer learning on top of our general embedding model and provide a very quick custom trained model. And again, here's an interface, Clarifai interface showing some images clustered. So I'm starting to build up a set of concepts and label them for some quick training. Basically, I can label in the UI on the order of 5 or 10 images of each class, and Clarifai behind the scenes will apply things like data augmentation, will apply some class imbalance control to try to make sure your model isn't too biased depending on the data that you put in. We provide a few levels of controls to say, are these concepts that I'm trying to recognize mutually exclusive or not? But because we're trying to be very efficient with your data, we cheat a little bit with the test set. So, of course, as a good machine learning person, if you have lots of data, you'll hold out 20% for training, 20% for testing, 20% for validation, and use maybe 60% of your data on training. If you have 3 examples of some class, then we can't afford to hold out 1 example for test and 1 example for validation, so we cheat and we do some cross-validation when you're limited in the amount of data. But basically, once again, we make it possible to train really fast on top of embeddings. And so if you deployed first, you used a pre-built model initially and you got some level of accuracy. Then you have a few examples because you had some users and you can label those examples, and then you can build a quick trained model on top of that. And that happens very quickly, and now I have a more accurate model, and I didn't have to write any code at this point. In the area of few-shot learning, I do want to mention that we do this category traversal. We have this category traversal paper, which was where we studied things and tried to figure out what are the invariances and what are the things that we're trying to learn within a category and what things distinguish between categories. And in general, what I'm trying to work through is this progression. So Clarifai will support millions of images. We build a large base model on top of that. We also build pre-built models on top of that. But if you have a little bit of data, then we can take off this layer and do your own custom model on top of that. And that gets you a set of labels. And if you want to use that in the rest of your system, then maybe you might build a structured AI model on top of that. And so that's what I'm showing in this figure, where At the bottom, I tend to need lots of data, and at the top of the figure, I have less data requirements and I have fewer parameters that I'm trying to train. So now if we're using the deploy first methodology and we used a pre-built model and we then got some data and we then built a custom quick train model and we got more data and we're getting to where we can actually get lots and lots of data, then we fall into an area where we can do active learning. And Clarifai provides a collection of tools to help that. We have collectors to help pull out some of the data that is submitted to the models as you go so that better models can be built. We have a scribe tool, which is our labeling tool, and the scribe tool supports some automatic labeling, so we can use the models that we've already built to label data that's coming in unsupervised learning. And there's an entire talk about this in the session done by Matt Zeeler. I'm just going to talk about one example where we did this ourselves internally. So we had a non-safe for work model. It was built by training actually on a lot of data, but we deployed it and got a lot more data because it's amazing how much not safe for work data is out there, and was submitted to our models as part of a moderation process. And so we get a bunch of data that's coming in, and we send some of that data. We decide the model is confident enough that we're just going to automatically label that as additional examples. And so if you think back to when I was talking about the nearest neighbor algorithm, the more examples that we have, the better a match we can do. So getting in these examples that the model is already getting right, but including those in our future training, that enables us to do a better job on images that are closer to those examples that we got right, and gets us closer to some examples in the future that maybe we didn't previously get right. So some examples that come in, we can do that. Some examples maybe the model isn't sure about, and those are the most valuable examples to label. So we can set up a workflow that pipes some of those off and has hand labeled, and then we can retrain a model and you can repeat this. So this is an example where our original model was trained with almost 1 million samples and had a very high accuracy. So once you're into the 90s in terms of accuracy, it becomes harder and harder to get the right answer. And in fact, if you think about it, with something that's not safe for work, there's a lot of fine-grained distinctions, and humans have a hard time agreeing on exactly which images are safe for work and which images aren't. And so then you have to write a whole set of procedures that say, oh, if it includes this, then it is, but if it's done in this way, then it's not. And you end up having the humans having to do this set of logic, whereas the computer is just able to do things based on example. So we were able to take our 1 million training samples, and then we were able to get another 1 million items, and label just 10% of those, and really push the accuracy up a significant amount. When we consider that a 95% accuracy, if you consider that there's going to be some errors in the test set and there's some errors in the training set, really those last few percentage points in any model are very, very hard. And so by doing just 10% more data, we were able to push a couple more percentages on the accuracy, which was huge. This is maybe an aside, but another thing that's of interest to us, there's work now on trying to select the most important things. So right now, maybe we're able to select based on the confidence of the model, but actually we should select in a much more intelligent way. And there have been work, the Data Shapely paper was an interesting one that sort of showed that if we train on the right subset of data, we can get more accurate more quickly. That one was not so practical because of the computation time to figure out which portion of the data was the right one to train on. But there have been recent work to do a better job of even that. So equitable evaluation of data for machine learning has a reinforcement learning approach to do things. And from our point of view, I think this can also be done not on individual samples, but on types of data or subsets of the data. And thus we can, again, speed up the data by making the right collection and training on the right subset, and more importantly, labeling the right subset of the data. So now I want to wrap things up by stepping through the different components of the Clarifai platform that help with us being data efficient. So this diagram shows the different pieces of the Clarifai platform. And on the left-hand side in the middle, we handle the management of data. So we upload some amount of data. A traditional machine learning project might upload lots and lots of data. Then send it to Scribe, our labeling tool, to label lots and lots of data. A traditional machine learning project would probably skip this search session, go straight to training, which is our Enlight product, and then to Armada, which is basically we've deployed the model and we run it for you and we scale it up and down for you depending on your usage limits, that you're receiving. And finally, if you have some additional logic, then we have the mesh product, which allows us to have workflows to build on top of that, the outputs of the model, which might be used, for example, for the active learning thing. So that's a typical pattern, but as I described, what happens is you might not even start at the data stage. You might deploy first, which means that I'm using a Clarifai pre-built model and using the Armada product to just handle all the predictions that I'm getting, and I'm using the workflows to collect data. And once I have a little bit of data collected, then I can use the search product to go through and figure out what classes I want to label, and then I can use the Scribe product to label those classes, and then I can again use the training product to train those data and build a better model, and then I can iterate this cycle. So basically, what we should be able to do is, instead of going from a traditional machine learning project where we spend a couple months collecting data, a couple months labeling data, and a little time preparing the data, and then iterating on these ideas, what loss function should I use? What learning schedule should I use? What architecture should I use on my large pile of data? And then, and only then, finally deploying it and finding out that it doesn't work. Instead, what I should do is I should build a model quickly. Maybe it's a few-shot model that I built without any code. I deployed it right away. I started collecting the real data. I figured out where it was working and where it wasn't. I used that to select the data that I needed to actually label. I didn't need to label all the data that I really thought I did in the first part. And I iterate at each time having a better model. And so accuracy gets better over time. And really, one of the key things about deploying first is a lot of machine learning projects are going to fail, not necessarily because of the machine learning. They're going to fail because even with the best machine learning, there's something else that's going wrong downstream. Oh, I realized even if I have perfect labels, I can't do the thing that I wanted. And so by deploying first with a pre-built model, I reduce my costs and I let my effort be about the end application and about what the user cares about rather than about the details of the machine learning. This is one of those diagrams that shows that there's a loop. It's still biased by putting the input on the left-hand side and suggesting input label train deploy, whereas I'm advocating that we start on the right-hand side, we deploy first, we figure out how that works in our product with the mesh, what workflows we need, and we use that to feed back to either data labeling or as a need to actually go out and explicitly collect some data. But hopefully we don't even have to collect data. We collect all our data from the deployed model, and we just do deploy, label, train, rather than collect data, label, train, deploy. So here are the things I stepped through. I stepped through using pre-built models, using the general model, maybe a subset of the model, using the general model to generate feature vectors, visual search, which I can start using when I have at least one example per class, Quick training, which I can do once I have, say, I can do it with 5 or 10 examples per class, but really better if I have 20 to 100 examples per class. Deep training when I have lots of data, and active learning when I have unlabeled data. So basically the call to action is visit clarifai.com, use less data, and deploy first.